optimization. This, we get into real-world calculus here. Like, most of the time when students ask, when are we going to use this in the real world? The answer is usually, well, either we have to make something up, or you have to be an engineer, or it's just, you're not really going to. But this, depending on your field, but this is, people use calculus to optimize things, to make things either cheaper, or to maximize their profits, or to use less materials, which is money as well. So this is real stuff that we're doing today. Let's do a little reminder here. There's a little piece of a graph. We'll say that's point A and point B. Make a little table, and we're going to start with the conclusion first because we can tell from the picture. You can tell from the picture that A is a relative max and B is a relative min. What's f prime at A? What's the derivative at A? 0. There's a horizontal tangent line there. What's f prime at B? 0. Okay, we've done that before. If f prime is 0, we have a potential max or min. So optimizing means we're going to be searching for maxes and mins, so we'll be looking for where f prime is 0. The trick is you can't just stop there, because if all you know is that f prime is 0, you don't know if you got a max or a min. What's the second derivative at A? Yes, you mean negative, because it's concave down. And the second derivative at B is positive because it's concave up. This is the second derivative test. If the first derivative is 0, then the second derivative will tell us, or can tell us, well, is it a min or is it a max? And so it's this second piece that people mess up today. Like getting the first derivative, setting it equal to 0, that's easy. We've done that enough times. We've got to remember to check the second derivative to know if we've got a max or a min. Right? This could be a major problem. If you're trying to maximize your company's revenue, but you forget to check the second derivative, what if you accidentally minimize your company's revenue? Well, that's a major mistake that you just made. So we've got to remember to check the second derivative to verify, okay, are we at the bottom or are we at the top? And depending on the problem, we might want to be at the top, we might want to be at the bottom, depending on what we're trying to do, but we need to make sure we know which one we're at, because just looking at the first derivative is not enough to know. List those as some steps. Set f prime equal to 0, solve for x. We've done that. This is why long ago, when we were first learning different derivative rules, the assignment would ask questions like, where does it have a horizontal tangent line? Or where is the derivative 0? Man, what is so special about that? Nobody asked that, but you should have been thinking that. And the thing that's special about that is, well, that's where the max and mins are. So now we're going to use that idea to find the max and the min. And then number 2, well, we need to figure out, is it a max or a min? And the sign of f double prime is usually the way to go. You can do the first derivative test as well, where you look at increasing, decreasing intervals. That works. But most of the time, taking a second derivative, especially if it's a polynomial, you know the second derivative is even easier. And so we'll go with that route. All right, example problems. 1, 2, 3 examples. Don't get too excited though. They're all kind of long because it takes a while to do all these steps. An open box is made from a 16-inch by 30-inch piece of cardboard. What size squares, copy it down, we'll talk about it in a minute. What size squares cut from the corners will maximize volume? Of cardboard, and if we cut squares from each corner, then we could fold it up and make an open box. And we want to figure out, well, what's the biggest volume we could make this box? Because if I make my squares really, really small, well, then the bottom areas would be big, but the walls would be short, and so that wouldn't be a whole lot of volume. If I cut my squares really big, then the walls would be taller, but for every inch or so, or each time I make the walls taller, I make the base smaller. And so somewhere in there's this perfect spot that maximizes the volume of this open box. Does that make sense? Do you understand what the question's asking and how this problem is working? Okay. So now we got to use calculus to figure out, well, how big do I need to make the square on each corner so that when I fold it up, I've got the most volume possible. Maximize volume. All right, well, let's draw a picture of the box, or of the rectangle, I guess I should say. And we want to cut corners. Cut those corners out, and then fold up what's left. To make a box, an open box. Let's see here. The full length was 30. And the full width was 16. All right, volume. What is what's the equation for volume? So forget about this picture, just in general, what's the equation of volume? Okay, so like the area of the base times the height, or length times width times height. So however you want to think about that. Length times width times height. Except that I need to be careful, my length isn't 30. I mean, after I fold up the box, it's not 30 anymore. So I need to figure out, it says what size corners. So let's say these corners are all just x by x. I'm going to cut an x by x corner. going to cut an x by x corner from each side. When we do that, what will the length equal? How long will...
30 minus 2x.
Yeah, the length then will be 30 minus 2x. Because we're cutting x off of each end. Be careful with cutting it off of each end. And the width, 16 minus 2x. And the height, once I take the corners and fold them up, then the height is x. It takes a little bit of visualizing what's going on here. When I fold those up, my height will be x. So my volume is 30 minus 2x times 16 minus 2x times x. Put that where you can see. That's what I want to maximize. If I want to maximize volume, I need to take the derivative of volume and set it equal to 0. I don't want to take the derivative of it right now because that would be awful. Product rule, but twice. Let's multiply this out. So I'm going to distribute the x to one of them, not to both of them, because then that would be multiplying by x squared. So the x to one of them, and then we'll FOIL. Again, this is one of those where you got to pay the price somewhere. You can pay the algebra price by FOILing, or you can pay the calculus price by having to do product rule. Either one's fine. Most people would rather pay the algebra price. So let's see. First, 16 times 3 is 48 with a 0, so 480x. Outside, minus 60x squared. Inside, minus 32x squared. And then last, plus 4x cubed. Let's clean that up a little bit. So 4x cubed minus 92x squared plus 480x. That's still volume. I haven't taken a derivative yet. That's just me doing some algebra to clean things up. So I have a clean expression for volume. All right, so let's take its derivative, because we want to find those places where it reaches a max or min. In this case, we want a max, because we want to maximize the volume. 12x squared minus 194x plus 480. What did I mess up?
184x.
Thank you. 184x. That looks terrible. Well, it doesn't look terrible. It wasn't hard to find. What's going to be terrible is when we set it equal to 0. This is where a calculator... Optimization problems are almost always calculator problems because you get some weird numbers. It would be nice if all of those were divisible by 12. Let's see. Well, I'm trying 12 first because that would be great.
184 divided by 12 is 15.
Yeah, that doesn't work. They are definitely all divisible by 4, so let's back up and do 4. Better than nothing. So 3x squared minus 46x plus, I don't need a calculator for that one, 120 equals 0. Well, it's not great, but it's sure way better than 12x squared. So I'm sure hoping this factors, because if it doesn't factor, I'm stuck using quadratic formula. Don't really want to do that. I mean, if you have to, you have to, but I'd like to, I hope it doesn't. Factors of 120. Let's see. Usually it's like the middle factors. It's rarely the extreme factors of 1 and 120, 2 and 60, 3 and 40, 4 and 30, 5 and something. 20 divided by 5. 24. 6 and 20. 7 probably doesn't work. 8 works. 9 probably doesn't work. 10 works. We got all sorts of options here. Plus we have to pair it with the 3. Or one of them with the 3. Let's see. They both need to be negative. So that at least takes a little bit of the guesswork out of it. And whoever's across from 3x is going to be multiplied by 3.
It's 10 and 12, and 12's getting multiplied by 3.
So a suggestion to put the 12 across from the 3. I put it in pencil because I trust whoever said that. Let's see, that would be negative 36 and negative 10. Yeah. Whoever said it over there.
Oh, something like that.
So x equals 10 thirds. And x equals 12. As possible maxes or mins for this problem. Back at the picture, x is either 10 thirds or 12. Anything stand out at you for 10 thirds or for 12? What's that? Why can't we do 12?
Because we have to use 16 minus 2x.
Right. Sometimes you get some funny answers. Like if I cut 12 inches from both sides of a 16-inch long piece of cardboard, like that's not going to work. Like mathematically something happened where it worked, but like if I'm holding a piece of cardboard and I'm cutting more than half from each end, that box is not going to work. So I can throw out 12 without even checking anything because that doesn't work. The width is 16 minus 22 times 12, sorry. So the width would be negative something, negative 8. Good. Yeah, mathematically it worked, but I can't do that. So I can throw out 12. I don't have to worry about 12. So I'm hoping 10 thirds is the answer. X equals 10 thirds, question mark. But I need to check to see if it's a max or a min. So let's do a second derivative. Second derivative, again, just to check to see. I'm hoping, if I want this to be a max, I'm hoping my second derivative will be negative, but we'll see. 24x minus 184. So at x equals 10 thirds, grab a calculator. 24 times 10 thirds minus 184. The second derivative is negative 104. So what does that mean in terms of concavity? Concave down, or V is concave down. So at x equals 10 thirds, we've got a horizontal tangent line, but we're concave down. So x equals 10 thirds is a max. Important in all calculus questions, but especially in these, is make sure you answer the question, because we could ask 3 or 4 different things about this. The question was, what size squares should we cut? So our square should be 10 thirds by 10 thirds. It would have been real easy to ask, what is the volume? What is the maximum volume? And then we would have had to plug that back in. But it didn't ask that, so we're good with the 10 thirds. Questions on that one? Set up the equation, take a derivative, figure out where it's 0, but then check to make sure you got a max or a min. Example 2. This is a classic calculus problem, updated to include a current fictional hero from Netflix. Anybody watch Longmire? Shameless plug. It's a good show. Fun show to watch. And the problem that goes with this is one that every calculus class in the history of the world has looked at. Without Longmire, though. Longmire has 200 meters of fencing. For a rectangular horse pen. Because, of course, he's a sheriff out west. He used to build a pen for his horses. Somehow he's arranged to get this 200 meters of fencing, and he wants to know, how do I best arrange this so I get a maximum area for his horses? A rectangular horse pen next to his house. And we want to find the maximum area of the pen. Okay, if it wasn't next to his house, do you know what the dimensions would need to be, or what shape it would be to maximize the area? A square. Even better would be a circle, but it's probably hard to mold your fence into a circle. That would maximize the area. But assuming he wants a rectangle, if it was by itself, you'd want a square. Because, if it's long and skinny, then there's not much area. If it's tall and short, there's not much area. You'd want it to be a square. But that's not the case. So he's got his house, and so he doesn't need fence for his house. He needs his fence to look something like that. Where this is his house. So he's smart enough to use, I'm going to use my house for one of the fences. That way I don't have to use fencing for it. I can get some more area out of it. So it's possible there's two different dimensions here. I mean, maybe it turns into a square. It won't, but we don't know that ahead of time. So let's call that X and Y, assuming that they're going to be different. So the maximum area, the area would just be X times Y. That's what we want to maximize. That's what we want to take a derivative of. But I don't really want to, if I take a derivative of that, that's got two variables in it, so I'd be using product rule to start with, and then I'd have dx and dy. I don't want to mess with this. I need a helper equation to get rid of x or y. So what else do I know about this problem that would help me in terms of x and y?
2x plus y plus 200.
Yeah, I know my total is 200. So 2x plus y equals 200. Books, people online will call these the primary equation and the secondary equation. You don't really have to know those names, but the primary is the one you want to take the derivative of. The secondary is like the helper equation. Because I don't want to take a derivative of xy, I would like to clean that up. And I can do it as long as I have a secondary equation. So I can solve for x or y, doesn't matter, and plug into the other one. You got a preference of what we should solve for? I think there's an easy choice. Yeah, y would be easier than x, and either one would be that hard. But let's solve for y. 200 minus 2x. And then we can substitute that into the primary equation. And now we have an equation with just x's in it. It's going to make life a lot easier. So area is 200x minus 2x squared. Still really haven't done any calculus on this problem. This is all algebra prep work to get ready to do the calculus. This is what I want to maximize, so this is what I'll take the derivative of. So dA dx, or just a prime if you want to make it easier to write. 200 minus 4x. Again, because maximums happen and minimums happen at places where the derivative is 0. So x equals 50 would give me a derivative of 0. But I don't know yet if that's a max or a min. Right? I would hate for Mr. Longmire to minimize the area of his house, or of his pen. So let's do a second derivative. Second derivative is negative 4. Well, okay, so this equation is always concave down. So yeah, we found a max. So x equals 50 maximizes the area. But what did it ask for? Find the maximum area of the pen. Okay, so we're not done yet. I mean, we're done with the calculus, but we need to answer the right question. The area is x times y. I know 50. Y we said was equal to 200 minus 2x. So y would be 100. So 50 times 100 would be 500 with another 0. 5,000, and then whatever units we were in, meters squared. Would be the most area that Sheriff Longmire could get out of that 200 meters of fencing. Super common problem. We like to also, we can mix them up and say that we want to like maximize the area of 2 pens. Maybe you need, a cage for your cattle and for your horses separately. And so you just have to kind of draw it out and figure out, well, that one would be 3x plus 4y. Maybe you got 3 different kinds of animals. And so there's no set formula. You just have to draw it out and figure out how many x's and how many y's you got to make it work. So that would be 4x plus 6y equals however much fence you have. So we can tweak these kind of problems, and you can bet that there'll be one something like that on the test. All right, one more. Last one. Example 3. A piece of wire 40 centimeters long is cut in two pieces. One piece we're going to turn into a circle, and one piece we're going to turn into a square. The question then is, find the lengths of both pieces to minimize the total area. Yes, this is going to be a hard one. This is going to be a weird one. So we'll start with a piece of wire that's 40 centimeters long. We're going to cut it somewhere and bend one of the pieces into a circle and the other piece into a square. A circle. Let's see, that area is pi r squared. If we make it into a square, that area is side squared. And the total area then would be pi r squared plus s squared. So that's our primary equation. That's the one we want to take the derivative of, but not yet because we got r's and s's in there. So we need a helper equation, a secondary equation. And it would have to do with that 40 centimeters long thing. So 40, you know what's going to add up to 40? Not in terms of formulas, but just in terms of letters. You know what's that? It won't be r plus s because there's r, the circumference and the perimeter. In fact, I'll just use the perimeter for both of them here. So the perimeter is 2 pi r and the perimeter is 4s. And the two perimeters have to add the 40 because that's what you're making you're using the 40 centimeter wire. So the perimeter of the circle plus the perimeter of the square will add together to be 40. Let's see, the perimeter of the circle is 2 pi r. Perimeter of the square is 4s. And it may not look like it yet, but we're almost there because this is an equation with r and s. So I can solve that for either one of them, plug it into this one, and take a derivative. Like the algebra is going to be ugly, but I think I'm set up to solve this problem. Do you want to solve for s or for r? Which one looks easier? S, I would agree, so you don't have to divide by pi. We can't get rid of the pi, but let's solve for s. So 4s equals 40 minus 2 pi r. We divide by 4, we get 10 minus pi r over 2. Well, yeah, not great, but I think better than the other way around. So with our helper equation, we can now express the area as pi r squared plus 10 minus pi r over 2 squared. Yeah, that's still area of the circle plus area of the square. Alright, I want to take the derivative of that. I'm at the place where you can pay me now or you can pay me later. I can square that out and pay the price in algebra world and make my calculus a little bit easier. Or I could leave it alone and pay the price in calculus world with the chain rule. I don't want to entertain suggestions because I know which one I want to do. It might be different than the one you want to do. Do you want to pay the price in algebra world, square it out, or do you want to pay the price in calculus world? I was afraid that's what you'd say. I think this is not a hard calculus one to do. It would just be 2 times all that to the first times the derivative of all that. So squaring it out, you're going to have, I don't want to square it out. I think I'd rather pay the price in calculus. If you want to square it out and do the algebra, you're right that the calculus later would be a little bit easier. But I don't think the trade-off is worth it. So I'm gonna work in calculus land here. So derivative of a, well, the first one's easy, 2 pi r. The second one, remember this is like the derivative of the pink triangle squared. So it's 2 times the pink triangle. Chain rule times the derivative of the pink triangle. Would be negative pi over 2. Because the derivative of r would just be 1. So negative pi over 2. So I think that was easier in calculus world than in algebra world. But if you'd rather square it out, it's okay. Okay, I've still got to pay the algebra price here. Let's see. What do I want to do? Set it equal to 0. The 2's will cancel. So it's a little bit of something. Then I'll distribute the negative pi. So negative 10 pi plus pi squared r over 2. Man, that's lovely. By the way, if you had done the algebra stuff at the front end and then taken the derivative, you should end up right here. So either way, you should get there. Alright, how in the world do we set that equal to 0? Well, I mean, it's set equal to 0. There's an r and there's an r. So let's move the 10 pi over. This is all algebra now. For better or worse. We're going to switch to a calculator here in a minute because this is not going to be pretty. Let's factor out the r. And this is getting ugly, but we're almost there. So r is 10 pi over 2 pi plus pi squared over 2. Calculus book would probably clean that up. We're just trying to figure out what r is, so let's go to a calculator. Be careful with parentheses, as always, when using a calculator. So make sure you're dividing by the right set of stuff. Pi plus pi squared over 2. I believe that is it. By the way, your calculator has a fraction bar. I don't know if you know this or not. The alpha F1, the first option is a fraction bar. So if the parentheses are really messing with you, you can avoid some of them. Let's see, that should be the same thing. And it is. So if you like the fraction bar, it's there. If you can handle the parentheses, that's fine too. So 2.800 for R. And what was this? Centimeters. We need to check to see if this was, so there's our first derivative. Let's back up and do a second derivative to check to see if this is indeed, we're trying to minimize. So the derivative would be, the second derivative, 2 pi. What's the derivative of negative 10 pi? 0. Yeah, you think pi is a variable, but pi is not a variable. Pi is just a number. So the derivative of negative 10 pi goes away. Plus pi squared over 2. I don't know what 2 pi plus pi squared over 2 is, but what was the point of taking the second derivative? What are we looking for here? Positive and negative. So I do know that it's positive. So let's see. Positive means we're concave up. A prime is 0, happens right there. So that means we found a minimum, which is what we were hoping for. A minimum. So that's kind of our verification. Let's go back. What did it ask for? Find the lengths of each of the pieces. Find the length of both pieces. So the perimeter of the circle would be the length of the circle piece. 2 pi r. We know r. .596 centimeters for the circle, or the circle piece. How about for the length of the piece for the square? There's a long way to do it and an easy way to do it. I did it the long way in the notes, and now I'm thinking, why did I do that? The whole piece is 40. We're using 17 and a half for one piece. So the piece for the square would just be 40 minus whatever we use for the circle. Not sure why I went the long way around in the notes. So 22.404 centimeters for the square. Now, I'll grant you, why in the world would you need to do that particular problem? I don't know. But again, this really is a place where business people can model profits based on the pricing that they set, or they can model expenses of materials based on all these different inputs. And so they've got to figure out, well, how many of these do we want to produce? If I produce too many, then I can't sell enough of them, or it costs too much. There's a lot of calculus in there that they can use to maximize their profits. All right, today's worksheet is sitting on my desk. It's called Worksheet 1. It's posted. If answers aren't posted already, I will post them in a moment. In fact, we may do one together here in a minute. So Worksheet 1, it should be posted in Schoology, and the answers will be posted soon if they aren't already.